So how do you train a system to catch a zero-day exploit without it completely panicking and deleting the CEO's presentation right in the middle of a massive all-hands meeting?
Right, which sounds like a joke,
It sounds like a punchline.
but I mean, if you are managing enterprise security for a Fortune 500 company,
Yeah.
that is the exact tightrope you are walking every single day.
Oh, absolutely. It's a daily struggle.
Yeah. Well, welcome to the deep dive. Today, our mission is to really decode the brain of an enterprise's digital defense.
Yeah.
Specifically, we are looking at the prevention policies within the CrowdStrike Falcon console.
And we've got a lot to get through today.
We do. We've got a stack of architectural documentation, deployment guides, recent cybersecurity research, you name it. We are going to explore exactly how these rules are built, how they're rolled out to thousands of machines, where they physically fall short, and how they're automated.
It's a massive topic. It is. So for you listening, think of this as the ultimate shortcut to understanding how organizations stop breaches without accidentally shutting down their own revenue streams in the process.
Yeah, because it really is a balancing act of risk versus availability. You want maximum security, obviously.
Right.
But if your security tool starts blocking legitimate revenue-generating business applications.
The business comes to a grinding halt.
Exactly. The system has to be aggressive toward novel threats, but heavily tuned to the unique environment it's operating in. And that tuning process, it all starts with how these prevention policies are structured fundamentally.
Right, because before we can apply the rules, we have to understand what the rules actually are. I mean, in the Falcon console, a prevention policy is essentially the master playbook.
A central brain.
Yeah, it defines what activity is going to trigger a detection, which is, essentially just an alert popping up on a screen somewhere, and what is going to trigger an actual prevention, where the system actively steps in, terminates the process, and stops the threat cold.
And it's important to note, this is not a simple binary on and off switch. They use machine learning sliders.
Sliders, right, not switches.
Right. The ML sliders are the absolute core of the prevention logic. Administrators use these to set the sensitivity level for both the sensor's internal machine learning, which operates locally on the machine, even if it's offline, and the cloud-based machine learning.
The cloud ML that leverages the global threat graph, right?
Exactly. And you can adjust these sliders from disabled all the way up through cautious, moderate, aggressive, and finally, extra aggressive.
And moderate is the recommended default for most production environments. But, I mean, you don't just walk into a company on day one, deploy the sensor to 50,000 machines, and just flip the switch to moderate.
No. That's a terrible idea.
Yeah, there's a very deliberate three-phase approach to rolling this out, right?
Yeah, you absolutely cannot just flip the switch. If you do, you will break the business. Phase one of the rollout is monitor-only coexistence.
Monitor only.
Right. This provides minimal active protection from the Falcon sensor itself, but it allows the sensor to sit quietly alongside any legacy antivirus the company might still be running.
So it's just watching.
Exactly. More importantly, it establishes a behavioral baseline. The system learns what normal day-to-day operations actually look like in that specific environment. It gives the security analysts time to triage false positives before any actual blocking occurs.
Okay, let's unpack this. Phase one is kind of like moving into an old, drafty house. You don't just grab a caulk gun and start sealing every gap the minute you walk in the door.
Right, you'd make a mess.
Yeah. You wait for a cold, windy day to feel where the drafts are actually coming from. Because if you just start sealing things blindly without understanding the airflow, you might accidentally caulk the front door shut.
Yeah, it captures the risk perfectly. You caulk the front door shut and, well, nobody can get to work.
Exactly.
Once you establish that baseline and tuned out those initial false positives, then you transition to phase two. This is enhanced protection, turning on those moderate settings for both cloud and sensor ML.
And what's the timeline on that?
The standard deployment timeline suggests you should reach phase two within about 45 days. And then finally you move to phase three, which is full protection with comprehensive settings, ideally achieved within 90 days.
Okay, I'm stuck on something here, though. I'm looking at this 45-day window for phase two, and something just isn't clicking for me.
What's that?
Well, if we know there are vicious ransomware variants out there that can encrypt an entire hard drive in a matter of seconds, leaving the system in a monitor-only or cautious state for weeks feels incredibly reckless. Why not just max the slider out to extra aggressive from day one and block everything bad immediately?
Look, this raises an important question, and it's one a lot of executives ask. The answer comes down to the catastrophic nature of false positives at scale.
How so?
If you jump straight to extra aggressive, on a network of 50,000 machines. The machine learning model is going to flag any custom internal software your company uses that hasn't been seen by the broader world.
Oh, right, custom apps.
Yeah. Say you have a proprietary accounting application written 10 years ago by an intern. It behaves weirdly, it injects into memory oddly, and it's rare. The aggressive ML will just kill it instantly.
So nobody gets paid because the intern's code looks like malware.
Precisely. To manage that risk safely and to close that 45-day gap faster, administrators use a tool called the Machine Learning Prevention Report.
Oh, interesting. So how does that report actually bridge the gap?
It basically acts as a simulation engine. Before an administrator ever touches that slider in the console to increase the aggressiveness, they generate this report based on the baseline data collected during phase 1.
Ah, so it looks backward at what already happened.
Right. It shows them exactly what would have been blocked in their specific environment if they had been running at a higher ML level over the past week.
Oh, wow, that's incredibly useful. It's like a sandbox for policy impact.
Exactly. You look at the report and see, okay, if we move to aggressive today, we would successfully block these 50 instances of novel malware, but we would also kill our proprietary accounting software on 2,000 machines.
So you know exactly what's going to break before you break it.
Yep. It gives you the specific data you need to whitelist the accounting software, fixing the false positive, before you turn the slider up and cause a massive IT outage.
Okay, so we have the rules defined, and we have a mechanism to tune those sliders safely using the simulation report. But now we face a massive logistical problem.
Scale.
Yeah, scale. We are talking about herding cats on a corporate scale here. How do we actually apply these finely tuned policies to tens of thousands of dynamic endpoints without creating just a chaotic, unmanageable mess?
Well, you rely on host groups. In the Falcon architecture, you cannot assign a prevention policy directly to an individual host machine.
Really? You can't just pick a laptop and give it a policy?
No, managing individual policies for 50,000 laptops would be impossible to audit. Instead, you assign a policy to a host group, and you place the machines inside those groups. And as a failsafe, if a host isn't assigned to any custom group, it automatically falls under the default policy.
And it's worth noting, the system literally will not let you delete that default policy. I saw that in the docs. It is the bedrock of the entire deployment.
It is the ultimate safety net. Now, when building out your architecture, these host groups come in a few different flavors. You have static groups, where an administrator manually adds specific machines. You have dynamic groups, which populate automatically based on defined rules. And then you have static BID groups.
Yeah, I noticed the static BID groups are specifically recommended for API and automation workflows. Why is that? Like, why not just use the regular static groups and search by the machine's name?
Because host names change. Yeah, in a modern cloud environment or a large corporate network using DHCP, a machine's IP address or its hostname might shift constantly. If your automation script relies on a host name to apply a security policy, the script will break the moment the name changes.
So what does static BID use instead?
It relies on the agent ID, or AID. This is a unique, immutable cryptographic identifier assigned to the sensor when it is installed. It never changes, making it perfect for robust API integrations.
Okay, that makes sense for the automated edge cases. But going back to the dynamic groups, the ones that handle the bulk of a company's workforce, to categorize hosts efficiently so they flow into these dynamic groups automatically, administrators use tags, right? Specifically, sensor grouping tags.
Yeah, sensor grouping tags are the secret to scaling a massive deployment. They're basically injected as a command line parameter during the initial installation of the sensor.
So what does that look like in practice?
Well, when your IT provisioning team images a new laptop for the marketing department, the installation script includes a tag like Marketing Workstation. The moment that sensor comes online and connects to the cloud, the dynamic group sees the tag, sweeps the laptop into the appropriate group, and assigns the correct prevention policy.
Zero human intervention required.
Exactly.
Here's where it gets really interesting to me, though. We are dealing with massive scale and overlapping rules. A single machine could easily possess tags or attributes that match the criteria for two completely different dynamic groups.
Oh, all the time.
Right. Let's say one group dictates a very strict, extra-aggressive policy, and another group has a lenient, moderate policy. How does the system resolve that conflict?
That is where precedence comes in. Precedence is the conflict resolution engine for the whole platform.
Think of precedence like a strict corporate org chart for your policies.
Oh.
Policy number 1 is the CEO. Even if Policy 50 says you can wear jeans to the office on Fridays, if Policy 1 says suits only, you are wearing a suit.
I like that.
The lowest number has the highest rank and unilaterally overrules the others.
That analogy holds up really well. Precedence ensures a deterministic outcome. If a host accidentally lands in 3 different groups, the system doesn't freeze or guess. It simply looks at the precedence ranking of the policies attached to those groups. Lowest number wins. Conflict resolved instantly.
Okay, let me challenge the reality of this dynamic tagging system, though.
Go for it.
If the grouping is fully dynamic and heavily reliant on tags applied during that initial installation script, what happens when human error enters the chat?
Always does.
Right. What if an IT contractor makes a typo or uses the wrong deployment script and accidentally tags a highly sensitive crown jewel database server as a standard guest kiosk? Doesn't the policy just blindly shift, leaving your most critical asset protected by a weak, lenient policy?
You've hit on the exact danger of over-relying on automation. If a tag is applied incorrectly, the system will execute exactly what it was instructed to do.
It just blindly obeys.
Yes. It will sweep that database server right into the guest kiosk group and apply the lenient policy. This is why strict governance and layered architecture are required. You never rely purely on dynamic tags for your critical infrastructure.
So how do you layer it to prevent that?
You use the precedence org chart you just mentioned, combined with static groups. A standard best practice is to place your highest value assets domain controllers, critical databases, executive laptops into static groups that are assigned to the policies with the highest precedence.
Like precedence 1 or 2.
Exactly. Because static assignments require deliberate manual action. And because they are tied to the top-tier precedence, even if someone accidentally pushes a dynamic tag to that server later, the strict policy will never get overridden. The static high precedence rule always wins.
So you essentially hard-code the VIPs at the top of the org chart so they literally cannot be accidentally demoted by an automated process. I like that.
Saves a lot of headaches.
I bet. So we've established the rules, and we've organized the endpoints using tags and precedents, but the real world is messy. Sometimes the standard rules simply do not fit. We need to wander into the exceptions, the custom behaviors, and the environments where these rules physically struggle to apply.
Which brings us to the dark alleys of policy management.
Exactly. Let's start with custom IOAs.
Right. IOA stands for Indicator of Attack. This is a crucial pivot in modern defense strategies. Instead of relying on legacy IOCs, indicators of compromise, which just look for known bad file hashes or malicious IP addresses, custom IOAs allow you to target actual behavior.
Because attackers are increasingly, living off the land, they aren't dropping obvious malware files onto the disk anymore.
No, they're using what's already there.
Right, they're using legitimate administrative tools that are already installed on the computer, like PowerShell or WMI, to execute their attacks. A traditional IOC won't catch that because PowerShell itself is a trusted, digitally signed Microsoft application.
Precisely. You can't just block PowerShell company-wide. That would be a disaster. So you write a custom IOA.
How does that look?
You create a rule that says, okay, I know PowerShell is allowed to run, but if PowerShell attempts to spawn a specific unapproved child process while simultaneously making an outbound network connection to an external IP address, block that specific action immediately.
So you are isolating the malicious behavior without breaking the legitimate tool.
Yes, exactly.
But sometimes adjusting the behavioral rules isn't enough to solve the problem, and administrators are forced to reach for the nuclear option. SVEs, or sensor visibility exclusions.
Well, SVEs. Yeah, SVEs are incredibly risky. They are an absolute last resort, utilized almost exclusively for severe performance issues.
Why do they cause performance issues in the first place?
Well, sometimes you have a legacy, poorly coded business application that performs thousands of rapid file input-output operations. When the sensor tries to inspect every single one of those operations, it can clash with the application and just max out the machine's CPU. If the business unit is screaming that their app is unusable, an administrator might deploy an SVE.
To visualize this, deploying an SVE is basically like turning off the security cameras in a bank vault just because the blinking red recording light is annoying the tellers.
Oh.
You are completely blindfolding the sensor for those specified processes or directories.
It is a total blindfold. The sensor collects no telemetry, and it enforces no preventions for that specific path. It just looks the other way.
Which attackers love, I'm sure.
Oh, they count on it. You can guarantee that sophisticated threat actors actively map enterprise environments looking for those exact exclusions. If an attacker discovers that an SVE has been applied to a specific folder on a server, They will drop their payload right into that folder. They can operate, execute, and move laterally completely undetected by the sensor.
Wow. Okay, so we've talked about what happens when the sensor conflicts with a legacy application. But what happens when there isn't even time to install the sensor in the first place?
Ah, the cloud problem.
Yeah, let's move into the cloud and talk about ephemeral resources.
Hmm.
In massive auto-scaling environments like AWS or Azure, you have containers and virtual machines spinning up to handle a sudden surge in web traffic. They do their job, process the data, and then completely terminate 5 minutes later.
And this represents a massive blind spot for traditional agent-based security.
Because there's no time.
Right. Traditional prevention policies rely on an agent, the physical sensor software being installed on the operating system. But in an ephemeral cloud environment, if a Kubernetes pod or a container only exists for 3 minutes, there is literally not enough time for an installation script to run, for the agent to stabilize, connect to the cloud, download its assigned prevention policies, and begin enforcing them.
So are these ephemeral workloads just sitting out there exposed? Does this create a massive pocket of shadow IT where the security team has zero visibility?
It does, unless you shift your architecture. If we connect this to the bigger picture, this is exactly why the industry is moving aggressively toward a hybrid agentless versus agent-based paradigm. For those highly ephemeral environments where a runtime agent simply cannot survive the life cycle of the workload, you pivot to agentless cloud-level scanning.
How does that actually work without an agent, though?
Well, instead of installing software on the container itself, the security platform connects directly to the cloud provider's API. It takes continuous snapshots of the block storage and reads the configuration blueprints from the outside in. It scans the environment at the control plane level.
Oh, okay. So you are scanning the architectural blueprint of the building and the foundation, rather than trying to put a physical security guard inside every single room.
That's a great way to look at it. Agentless scanning gives you instant visibility across tens of thousands of short-lived resources. The second a container spins up, the API integration evaluates it.
And it flags issues immediately.
Yep. It tells you immediately if that container was deployed with a vulnerable configuration or an exposed port. Then you reserve your lightweight runtime sensors, the actual agents, for your persistent, highly critical workloads like databases and core application servers, where you absolutely need that deep, active, process-killing prevention capability. You weave them together to eliminate the blind spots.
Okay, let's step back and look at what we've built here. We have our ML sliders tuned via simulation reports. We have dynamic tags herding thousands of endpoints into precedence-ranked groups. We are deploying behavioral IOAs to stop living off the land attacks. And we are balancing agentless API scans with runtime sensors to secure ephemeral cloud instances.
It's a lot.
The complexity is staggering. I mean, human beings cannot manually track all of this.
Wow.
How do we automate the responses when things go wrong? And critically, how do we monitor who is altering our master rulebook?
You manage that complexity with Falcon Fusion SR. It is the orchestration engine built directly into the platform, designed to take the manual heavy lifting off the security operations center.
Oh.
It operates on a straightforward but highly customizable model. Trigger, condition, action.
Trigger, condition, action. So a specific event happens, that is the trigger. The system checks if certain contextual criteria are met, the condition. And if they are, it executes a predefined response, the action.
Exactly. And while people often think of SOSAR purely for responding to malware, one of the most powerful use cases is auditing the system itself. You can build workflows using audit event triggers specifically to monitor policy changes. If a prevention policy is created, updated, disabled, or deleted, that event serves as the trigger.
Which is vital, because if a sophisticated attacker manages to compromise a security administrator's credentials, the very first thing they will attempt to do is quietly disable the prevention policies so they can deploy their ransomware freely.
Right, they want to turn off the alarms before they rob the bank.
Exactly. So to track this, the platform relies on the activity audit log. It tracks the exact user who modified a policy, the exact setting they changed, and the precise timestamp.
It is the unerasable fingerprint of the platform. But Fusion SOR takes that log data and makes it actionable. The actions you can execute are extensive. A workflow can be configured to automatically send a rich context notification to a dedicated SOC Slack channel, generate a fully populated incident ticket in ServiceNow, or, if the condition dictates a severe threat, automatically network contain a host.
Let's pause on network containment because that is wild. That literally drops the firewall at the kernel level, cutting the machine off from the entire corporate network and the internet, leaving only a tiny encrypted lifeline back to the Falcon console so analysts can investigate. That is immense power.
It is.
What if we aren't quite ready to let the automation engine make that kind of business halting decision on its own?
That hesitation is incredibly common. Security teams are terrified of fully automated responses because a false positive could result in an automated workflow isolating a critical server and causing a massive outage. To bridge that trust gap, the platform includes a workflow step called request human input.
So what does this all mean? It's basically like setting up a digital tripwire combined with a manager's sign-off sheet. The system catches the anomalous behavior, gathers all the forensic context, prepares the ServiceNow ticket, initiates the lockdown sequence. But it taps an analyst on the shoulder before hitting the actual self-destruct button.
Exactly.
It pauses the workflow entirely until an authorized human receives a prompt on their phone or console and explicitly clicks approve, decline, or escalate.
It perfectly balances the speed of machines with the judgment of humans. You get the rapid triage and containment prep of automation, but you retain a human safeguard for the final, irreversible action.
I love the elegance of that. But let's look at the dark side of orchestration. If these workflows have the permissions to automatically network contain machines, send broad alerts, and execute scripts, what stops a malicious insider or, a rogue employee who is about to quit from simply writing a custom Fusion SOAR workflow to instantly isolate every machine in the company and shut down the entire network?
That scenario is heavily mitigated by strict role-based access control, or RBAC. The system does not allow just anyone to build or modify these automations. To even access the workflow builder, a user must be explicitly granted the Falcon administrator or workflow author role. A standard Tier 1 security analyst can view the alerts generated by the workflow, but they cannot rewire the engine itself.
And even if an administrator goes rogue, they can't hide it, right?
Exactly. Because of that activity audit log, every single modification to a workflow leaves an indelible record. If an insider tries to build a destructive workflow, the system records their exact identity. In fact, many advanced teams build a secondary SR workflow whose sole purpose is to trigger an alert if any of the primary security workflows are modified.
A workflow watching the workflows.
Yeah.
That is a brilliant layer of governance. Well, we have covered a massive amount of ground today. We started by defining the core architecture of prevention policies, exploring how to safely ease into active blocking using ML sliders, simulation reports, and the three-phase rollout.
It's quite the journey.
It is. We decoded the logistics of massive deployments using host groups, sensor grouping tags, and the ironclad conflict resolution of precedents. We navigated the edge cases, utilizing custom IOAs for behavioral threats, outlining the severe risks of SVEs, and adapting to ephemeral cloud environments with agentless scanning. And finally, we tied it all together by orchestrating the chaos with Fusion SOR, balancing rapid automation with essential human oversight and strict auditing.
It really highlights the reality of modern enterprise defense. It is no longer just about writing a better malware signature. It's about architecture, strict governance, and orchestrating thousands of independent moving parts so they function as a single resilient defense mechanism.
It is an entirely different paradigm. But before we wrap up, I want to leave you with a final provocative thought to mull over. We have spent this deep dive exploring how we use machine learning sliders to block threats, and how we use automated SOAR workflows to outpace human attackers. But adversaries are adopting and training their own AI models just as rapidly as defenders are. So, what happens when the attackers start deploying adversarial AI to silently probe an enterprise network, specifically analyzing response times to predict the exact ML slider levels of your prevention policies?
That's a terrifying thought.
Right. If an attacker's AI can dynamically map your customized blind spots, will tomorrow's prevention policies need to dynamically shift their own aggressiveness in real time, effectively playing an automated, high-speed game of chess against the attacker's AI before a human ever sees an alert?
It is a profound technical challenge, and it is likely the next major frontier in security architecture.
The goal was always to catch the zero-day threat without deleting the CEO's presentation. But soon, the architecture itself might have to decide how to outsmart an AI before that presentation is even written. Thanks for joining us on this deep dive. Keep questioning, keep exploring, and we'll see you next time.